Oh hey, didn't see you there. Hi, I am AntMan, and I want to talk to you about a very common quantum mechanical phenomenon in nature called tunneling. Let's consider that we want to move from this side of the wall to the other. We know that if we have enough energy to reach the top of the wall, we can move to the other side. But we will never make it if we don't have enough energy. This is an illustration of conservation law. In contrast, we don't require enough energy to reach the top of the wall in the quantum realm. We may tunnel through it to move from one side to the other. Something similar for access to platform 9 3/4. But to talk about this, we must first enter the quantum realm. Let's go! Tunneling is a quantum phenomenon in which particles penetrate a higher potential energy barrier than their total energy, as occurs in the process that caused the sun to ignite. Tunneling is more familiar with tiny particles, such as electrons and hydrogen atoms. However, this doesn't rule out the possibility of heavy atoms tunneling. There is evidence that it's essential to incorporate tunneling phenomena when calculating thermal rate constants, in processes involving heavy atoms such as carbon. But how are tunneling effects taken account when calculating rate constants? Quantum effects of tunneling and non-classical reflection are included in the so-called tunneling transmission coefficient, defined as the ratio between the quantum transmission probabilities to the quasi-classical transmission probabilities. Reaction rates are corrected by this coefficient. The most challenging aspect of calculating kappa is estimating the quantum transmission probability. But there is a solution. Eyringpy. Eyringpy is a program that uses the transition state theory and the canonical variational transition state theory to calculate rate constants. The upcoming version includes the zero curvature tunneling model to calculate the transmission coefficient. The WKB approximation is used to estimate the tunneling probability, and the Gaussian quadrature or trapezoidal rule is used to solve the action integral equation. You don't have to worry, Eyringpy does all the hard work. Eyringpy is user-friendly and fairly intuitive, even if you don't have any programming knowledge. Wigner and Eckart's models are already accessible in released Eyringpy versions, but this is not it. The small curvature tunneling model is also being implemented. Eyringpy multidimensional tunneling is coming soon.